Right now, as you sit here listening to this, every single cubic centimeter of empty space around you is doing something that no physicist on Earth can fully explain. It is pushing, not pulling like gravity, pushing. And this invisible, silent, relentless push is tearing the universe apart, accelerating the expansion of everything that exists, flinging galaxies away from each other faster and faster with every passing second. Here is the part that should keep you up at night. Albert Einstein predicted this. Over 100 years ago, he wrote down a single term in his equations, a small addition, a tiny Greek letter, lambda, that described exactly this kind of cosmic repulsion, and then he threw it away. He called it the biggest blunder of his life. But here is the twist that makes this one of the most extraordinary stories in all of science. That so-called blunder turned out to be one of the most prophetic ideas in the history of human thought. The force Einstein imagined and then rejected now accounts for roughly 68% of everything that exists, more than all the stars, all the planets, all the gas and dust and dark matter combined. The universe is mostly made of something Einstein was embarrassed to have invented. This is the story of the cosmological constant, and it begins not with equations or telescopes, but with a question that has haunted human beings since the first time someone looked up at the night sky and wondered, is the universe changing, or has it always been like this? For most of recorded history, the answer seemed obvious. The cosmos was eternal. It was unchanging. The stars wheeled overhead in their fixed patterns, and the heavens were the very definition of permanence. The ancient Greeks, the medieval scholars, the natural philosophers of the Enlightenment. Nearly all of them assumed the universe was a static, timeless stage on which the drama of existence played out. This assumption ran deep. Aristotle, writing in the 4th century before the Common Era, argued that the heavens were made of a perfect, unchanging substance, entirely different from the corruptible matter found on Earth. He called it ether, the 5th element, and he believed it was eternal and immutable. The stars in Aristotle's picture were fixed in a crystalline sphere that rotated around the Earth with perfect regularity. Change happened on Earth. Change did not happen in the heavens. This view persisted, with modifications, for nearly 2,000 years. Even after Copernicus displaced the Earth from the center of the solar system, even after Galileo pointed his telescope at the heavens and discovered mountains on the moon and satellites orbiting Jupiter, the basic assumption of a static, eternal universe remained largely unchallenged. The cosmos might be larger and more complex than the ancients imagined, but its fundamental character was permanent. Stars were born and stars died, but the universe as a whole endured. Isaac Newton, whose law of universal gravitation described how every mass in the universe attracts every other mass, assumed that the cosmos was infinite and essentially unchanging. He had to, in a sense, because his own theory created an uncomfortable problem. If gravity pulls everything toward everything else, then why hasn't the universe collapsed into a single point? Newton was aware of this difficulty. In a famous exchange of letters with the theologian Richard Bentley in the 1690s, Newton attempted to address it. His answer was essentially to argue that in an infinite universe, uniformly filled with matter, the gravitational pulls from all directions would balance out. Every point in the universe would be pulled equally in all directions, and so the net force would be zero. It was not a particularly satisfying answer. Later mathematicians would show that Newton's argument contained a subtle error. In an infinite, homogeneous distribution of matter, the gravitational force at any point is actually undefined, not zero. But for over 2 centuries, nobody had a better framework for thinking about these questions. And then, at the dawn of the 20th century, a young patent clerk in Bern, Switzerland, began thinking thoughts that would demolish the old picture of the cosmos entirely. Albert Einstein was, by the early 1900s, already an unusual figure. Born in 1879 in Ulm, Germany, he had shown flashes of brilliance as a student, but also a stubborn independence that alienated some of his professors. He failed to secure an academic position after graduating from the Swiss Federal Polytechnic in Zurich. And so, he took a job at the Swiss Patent Office, evaluating technical applications by day and doing physics in his spare hours. It was in those spare hours that he changed the world. In 1905, his so-called miracle year, Einstein published 4 papers that would each, individually, have been enough to make a career. One explained the photoelectric effect, showing that light comes in discrete packets of energy called quanta. Another provided definitive evidence for the existence of atoms by explaining the random jittering motion of tiny particles suspended in a fluid. A third introduced the special theory of relativity, revealing that measurements of time and length depend on the relative motion of the observer. And a fourth, almost as an afterthought, showed that mass and energy are equivalent, captured in that famous expression, E equals mc squared. But Einstein was not finished. Special relativity dealt only with objects moving at constant speeds in straight lines, what physicists call inertial frames of reference. It said nothing about gravity. It said nothing about acceleration. And Einstein knew that any complete picture of reality would need to account for both. So he set out to build a new theory of gravity, one that would supersede Newton's and encompass the strange, new insights of relativity. It took him 10 years. A full decade of agonizing mathematical struggle, false starts, moments of exhilaration followed by crushing disappointments, and a mental effort so intense that Einstein later said it nearly killed him. He worked with some of the finest mathematicians of his era, including Marcel Grossmann and David Hilbert. He explored exotic mathematical frameworks that most physicists had never encountered. The curved geometries developed in the 19th century by Bernhard Riemann and others, and in November of 1915, he finally cracked it. Standing before the Prussian Academy of Sciences in Berlin, Einstein presented his general theory of relativity. The equations he unveiled that autumn described a universe fundamentally different from anything Newton had imagined. In Newton's picture, gravity was a force, a mysterious, instantaneous pull that reached across empty space and tugged on distant objects. Nobody knew how it worked, not even Newton himself, who famously wrote that he would not feign hypotheses about the mechanism behind gravitational attraction. Einstein replaced this picture with something far more radical. Gravity, he said, is not a force at all. It is geometry. The presence of mass and energy warps the fabric of spacetime itself, bending it and curving it, and objects moving through this curved spacetime follow the paths dictated by that curvature. The Earth orbits the Sun, not because the Sun is pulling on it with some invisible rope, but because the Sun's enormous mass has curved the spacetime around it into a shape that guides the Earth along its elliptical path. As the physicist John Archibald Wheeler would later sum it up with elegant simplicity, matter tells spacetime how to curve, and spacetime tells matter how to move. The equations of general relativity are beautiful, but they are also ferociously complex. They are not a single equation, but a set of 10 interlocking equations, all tangled together, all nonlinear, meaning that the output of one feeds back into the inputs of the others. Solving them exactly is extraordinarily difficult, and in many cases impossible. But the theory was powerful. It predicted phenomena that Newtonian gravity could not, such as the precise amount by which Mercury's orbit shifts over time, the bending of light around massive objects, and the slowing of time in strong gravitational fields. Observations confirmed these predictions, and general relativity quickly became recognized as one of the supreme achievements of the human mind. But Einstein was not content merely to describe how gravity works in the vicinity of stars and planets. He wanted to apply his theory to the largest possible stage, the universe itself. And that is where things got complicated. In February of 1917, just over a year after completing General Relativity, Einstein presented a new paper to the Prussian Academy. Its title, translated from German, was Cosmological Considerations in the General Theory of Relativity. It was the first serious attempt to use general relativity to build a model of the entire universe, and it would become one of the most consequential and controversial scientific papers ever written. Einstein faced a problem. When he applied his field equations to the cosmos as a whole, they did not give him what he expected. He expected, as virtually every scientist of his time did, a static universe, an eternal cosmos that neither expanded nor contracted. This was not just a scientific assumption. It was deeply embedded in the philosophy and culture of the era. The idea that the universe might be changing, growing, shrinking, evolving on the largest possible scale. This was simply not part of the conceptual landscape, but his equations were telling him something different. They were telling him that a universe filled with matter could not be static. Gravity would cause it to collapse. Every bit of matter would attract every other bit, and the whole thing would come crashing inward. It was, in a sense, the same problem Newton had faced centuries earlier. But now it was encoded in the precise mathematical language of general relativity, and it was much harder to sweep under the rug. Einstein was deeply troubled by this. He had strong philosophical commitments to what he called Mach's principle, the idea that the inertia of any object is determined entirely by the distribution of all the other matter in the universe. He wanted his theory to satisfy this principle, and he wanted the universe to be finite, closed, and static. A universe that collapsed was unacceptable. So he did something remarkable. He modified his own equations. He added a new term, a small addition represented by the Greek letter lambda, which he called the cosmological constant. This term acted as a kind of repulsive force, a cosmic pressure that pushed outward and counterbalanced the inward pull of gravity. By carefully choosing the value of lambda, Einstein could produce a model of a universe that was perfectly balanced. Matter pulled inward, lambda pushed outward, and the whole thing sat in perfect equilibrium. He was not happy about it, even at the time. Einstein recognized that the cosmological constant was somewhat artificial. He later wrote that it had always given him a bad conscience, that he could not bring himself to believe something so inelegant was actually realized in nature, but it seemed necessary. The alternative, a collapsing or expanding universe, was simply too radical to accept. And so, the cosmological constant was born. A mathematical patch, a fudge factor, an admission that the equations needed a little help to produce the answer Einstein wanted. He published his paper, and the scientific world took notice. But almost immediately, the problems began. Only months after Einstein's paper appeared, the Dutch astronomer and mathematician Willem de Sitter found another solution to the modified field equations. De Sitter's solution described a universe that was completely empty, containing no matter at all, but which still had a positive cosmological constant. This was deeply disturbing to Einstein, because the whole point of Mach's principle was that spacetime should not have properties in the absence of matter. An empty universe with geometry and curvature felt like a contradiction of everything Einstein believed. De Sitter, born in 1872 in the Dutch town of Sneek, was an unusual figure in the scientific landscape of the early 20th century. He was comfortable working as a mathematician, a physicist, and an astronomer, which made him one of the very few people in the world capable of truly understanding and applying Einstein's general relativity. He had been appointed professor of astronomy at the University of Leiden in 1908, and he would later become director of the Leiden Observatory. His series of 3 papers in 1917, published in the monthly notices of the Royal Astronomical Society, effectively introduced general relativity to the English-speaking scientific world. This was no small achievement, because the First World War had severed most normal scientific communication between Germany and England. De Sitter's empty universe solution was not just a mathematical curiosity. In his 3rd paper, he pointed out something fascinating. If you introduced a single particle of matter into his empty universe, that particle would appear to be moving away from the observer. The cosmological constant, even in the absence of real matter, caused a kind of effective recession. This was the first hint, the very first glimmer, that the universe might not be as static as everyone assumed. Einstein was not pleased. He engaged in a lengthy correspondence with de Sitter, arguing that the empty universe solution was physically meaningless, that it violated Mach's principle, and that it should not be taken seriously. But de Sitter had planted a seed. The mathematical machinery of general relativity, even with the cosmological constant included, was pointing toward a universe in motion. Someone just needed to follow the mathematics where it led. That someone turned out to be a brilliant Russian mathematician working far from the centers of European physics. In a city racked by revolution, civil war, and famine, Alexander Friedman was born on the 16th of June, 1888, in St. Petersburg, to an artistic family. His father was a ballet dancer and composer. His mother was a pianist. Young Alexander showed extraordinary mathematical talent from an early age, and he obtained his degree from St. Petersburg State University in 1910. But Friedman's life was shaped by far more than academic pursuits. He fought in World War I as an aviator for the Russian Imperial Army, personally piloting reconnaissance missions, and even developing a mathematical theory of bomb trajectories that he verified during flights over the Austrian front. After the war, amid the chaos of the Russian Revolution and the bitter civil war that followed, Friedman returned to what was now called Petrograd and threw himself into an astonishing number of academic appointments simultaneously, teaching at the university, the Polytechnic Institute, the Institute of Railway Engineering, and the Naval Academy, all while conducting research on hydrodynamics, meteorology, and the new physics of relativity. In 1922, Friedman turned his formidable mathematical abilities to Einstein's cosmological equations, and he saw something that Einstein had missed. Friedman did not begin with the assumption that the universe was static. Instead, he explored what the equations predicted when you allowed the universe to change with time. He plugged in different values for the cosmological constant, different assumptions about the geometry of space, and he found an entire family of solutions that Einstein had never considered. Some described a universe that expands forever. Others described a universe that expands for a while, then contracts back to a point, then expands again, oscillating like a cosmic heartbeat. Einstein's perfectly balanced static universe was just one very special case among many, and a fragile one at that. Friedman wrote up his results in a paper titled On the Curvature of Space, and sent it to the prestigious German journal Zeitschrift für Physik. It was received on the 29th of June, 1922, and published shortly thereafter. Einstein was not impressed. He wrote a note to the same journal, received on the 18th of September, claiming that Friedman had made a mathematical error. The results concerning the non-stationary world, Einstein wrote, appear to me suspicious. In reality, it turns out that the solution given in it does not satisfy the field equations. But the error was Einstein's, not Friedman's. In December, Friedman wrote a careful, respectful letter to Einstein, walking through the calculations step by step and asking Einstein to verify them. Einstein eventually did. In a brief follow-up note published in 1923, he acknowledged that Friedman's mathematics was correct. But he added a dismissive caveat. While the math was valid, he said, it had no physical significance. The idea of an expanding or contracting universe was, in Einstein's view, merely a mathematical possibility with no connection to reality. It was a stunning misjudgment. Friedman had, in his quiet study in post-revolutionary Petrograd, unearthed the mathematical foundations of what would become the most important discovery in the history of cosmology. But recognition would come too late for him. In July of 1925, Friedman participated in a record-setting balloon flight, reaching an elevation of over 7,000 meters. 2 months later, on the 16th of September, he died of misdiagnosed typhoid fever. He was just 37 years old. He never knew that the expanding universe he had predicted on paper was the real universe. Meanwhile, far from Russia, another brilliant mind was independently arriving at the same conclusions. Georges Lemaitre was a Belgian physicist, mathematician, and remarkably, a Catholic priest. Born in 1894 in the industrial city of Charleroi, Lemaitre had served as an artillery officer in the Belgian army during World War I, witnessing firsthand the first poison gas attacks in history. After the war, he pursued both science and theology simultaneously, being ordained as a priest in 1923, and also studying theoretical physics under the distinguished English astronomer Arthur Eddington, who regarded him as a wonderfully quick and clear-sighted student of great mathematical ability. In 1927, Lemaitre published a paper in a relatively obscure Belgian journal, the Annales de la Société Scientifique de Bruxelles. The paper's title, translated from French, was A Homogeneous Universe of Constant Mass, and Increasing Radius Accounting for the Radial Velocity of Extragalactic Nebulae. It was, in essence, the same kind of expanding universe solution that Friedman had found. But Lemaitre went further. He was not just a mathematician exploring abstract solutions. He was a physicist and an astronomer who was aware of actual observations, specifically the measurements by the American astronomer Vesto Slipher, showing that the light from distant nebulae was shifted toward the red end of the spectrum, suggesting they were moving away from us. Lemaitre connected the theoretical prediction of an expanding universe with these observed redshifts. He even derived a relationship between a galaxy's distance and its recession velocity, anticipating what would later become known as Hubble's law. A full 2 years before Edwin Hubble published his famous results, but Lemaitre's paper, published in French in a journal that few international physicists read, was almost completely ignored. When Lemaitre met Einstein at the 1927 Solvay conference in Brussels and told him about his expanding universe model, Einstein responded with a remark that must have stung. "Your calculations are correct, but your physics is abominable." Einstein simply could not accept the idea of a universe in motion. His cosmological constant was supposed to prevent exactly that. The universe was static. It always has been. It always would be. But the universe did not care what Albert Einstein believed. On the other side of the Atlantic, a tall, athletic, pipe-smoking former lawyer was about to prove, beyond any reasonable doubt, that the cosmos was doing exactly what Friedman and Lemaitre said it was doing. Edwin Powell Hubble was born on the 20th of November, 1889, in Marshfield, Missouri. He was a remarkable figure, even apart from his astronomical achievements. As a young man, he was a gifted athlete, known for his skills in basketball, football, baseball, track, and boxing. He earned an undergraduate degree in mathematics and astronomy at the University of Chicago, then studied law at Oxford on a Rhodes Scholarship, fulfilling his father's wishes. But the law never held his heart. After a brief, unhappy stint practicing law, Hubble went back to school, earning a doctorate in astronomy from the University of Chicago in 1917. After serving in the Army during World War I, Hubble took up a position at the Mount Wilson Observatory near Los Angeles, California, home to the most powerful telescope in the world, the 100-inch Hooker telescope. It was here, in the thin mountain air above the sprawl of early 20th century Los Angeles, that Hubble would reshape humanity's understanding of the cosmos. His first great triumph came in 1923 and 24, when he identified a special type of pulsating star, a Cepheid variable, in what was then called the Andromeda Nebula. By measuring the pulsation period of this star, Hubble could determine its intrinsic brightness. Using a technique pioneered by the astronomer Henrietta Swan Leavitt more than a decade earlier, comparing the star's intrinsic brightness to its apparent brightness as seen from Earth, Hubble calculated that the Andromeda Nebula was far, far beyond the boundaries of our own Milky Way galaxy. It was not a cloud of gas within our galaxy at all. It was an entirely separate galaxy, a vast island of stars millions of light years away. This alone was revolutionary. Until Hubble's discovery, most astronomers believed the Milky Way was the entire universe. Suddenly, the cosmos was immensely larger than anyone had imagined. But Hubble was not done. Working with his colleague Milton Humason, a former janitor at Mount Wilson, who had risen through sheer talent and determination to become one of the observatory's most skilled observers, Hubble began systematically measuring the distances and redshifts of as many galaxies as he could. The redshifts had been building up for years, thanks primarily to the meticulous work of Vesto Slipher at the Lowell Observatory in Arizona, who had shown that the vast majority of the spiral nebulae had light that was shifted toward the red end of the spectrum, indicating they were moving away from us. Hubble combined his distance measurements with these redshift data, and in a paper published in March of 1929, presented a graph that would become one of the most famous in all of science. The graph showed a clear, linear relationship. The farther away a galaxy was, the faster it appeared to be receding from us. This was not the result of galaxies flying through space away from some central point, like shrapnel from an explosion. It was the fabric of space itself stretching, carrying the galaxies along with it. The universe was expanding. The implications were staggering. If the universe is expanding now, then it must have been smaller in the past. Run the clock backward far enough, and you arrive at a moment when all the matter and energy in the cosmos was compressed into an unimaginably hot, dense state. The universe had a beginning. When Einstein learned of Hubble's results, the impact was profound. He visited Mount Wilson Observatory in 1931 and met Hubble personally. According to reports from the visit, Einstein declared that the trip had changed his mind. The universe was expanding. The cosmological constant was no longer necessary. In the early 1930s, Einstein published 2 new models of the expanding universe, and in each case, he dropped the cosmological constant entirely, calling it both unsatisfactory and redundant. According to George Gamow, the brilliant Russian-born physicist who later played a central role in developing the Big Bang theory, Einstein once described the introduction of the cosmological constant as the biggest blunder of his life. Some historians have questioned whether Einstein used exactly those words, noting that Gamow was known for colorful storytelling. But the sentiment is consistent with what other physicists reported. Einstein was embarrassed. He had added an artificial term to his equations to prevent them from telling him the truth, and the truth had come out anyway. With the cosmological constant abandoned and the expanding universe confirmed, a new era of cosmology began. And at the center of this new era was a radical, almost unbelievable idea that the universe had been born in a single, cataclysmic event. Georges Lemaitre, the Belgian priest-physicist, was the first to push this idea to its logical conclusion. In March of 1931, he published a brief but electrifying paper in the journal Nature, proposing that the entire universe had begun as a single quantum of enormous energy, which he called the primeval atom. As the universe expanded, this primeval atom disintegrated, its energy spreading out and cooling, eventually giving rise to the galaxies, stars, and planets we see today. The idea was met with skepticism, even hostility. Arthur Eddington, Lemaitre's former mentor, declared that the notion of a beginning of the world was philosophically repugnant. Einstein, when he first heard the hypothesis, suspected that Lemaitre's religious convictions as a priest were influencing his science, a charge that Lemaitre firmly rejected throughout his life, always insisting that the physical beginning of the universe was an entirely separate concept from the theological idea of creation. But after meeting Lemaitre again in January of 1933 at the California Institute of Technology, and hearing him present his theory in detail, Einstein reportedly stood up, applauded, and said it was the most beautiful and satisfactory explanation of creation he had ever heard. The astronomer Fred Hoyle, who championed a rival steady-state theory in which the universe had no beginning and would have no end, dismissed Lemaitre's idea with a memorable insult during a BBC radio broadcast in 1949. He called it the Big Bang. The name, intended as a mockery, stuck, and the theory it described would eventually triumph, not through philosophical arguments or religious inspiration, but through a discovery made by two very puzzled radio engineers in New Jersey. In 1964, Arno Penzias and Robert Wilson were working at Bell Telephone Laboratories in Holmdel, New Jersey, using a large, horn-shaped radio antenna that had been built for satellite communications. They were trying to detect faint radio signals from space, but they had a problem. No matter where they pointed their antenna, no matter the time of day or the season, they detected a persistent, low-level hiss. It was coming from every direction, and they could not figure out what was causing it. They checked everything. They pointed the antenna at New York City to see if urban interference was the culprit. It was not. They looked for problems in the electronics. They found none. They even discovered that a pair of pigeons had been nesting inside the antenna, coating parts of it with droppings. They trapped the pigeons, cleaned the antenna, and checked again. The hiss remained. Frustrated, Penzias eventually learned through a colleague about a group of physicists at Princeton University, led by Robert Dicke, who were building a detector to look for something very specific, a faint glow of microwave radiation that should be filling the entire universe. If the Big Bang theory was correct, the physicist George Gamow and his collaborators, Ralph Alpher and Robert Herman, had predicted back in the late 1940s that if the universe had indeed begun in a hot, dense state, the radiation from that early era should still be detectable today, cooled by the expansion of the universe to a temperature of just a few degrees above absolute zero. When Penzias called Dicke at Princeton and described the mysterious signal, Dicke immediately understood what they had found. Legend has it that Dicke hung up the phone, turned to his colleagues, and said, "Well, boys, we've been scooped." What Penzias and Wilson had detected was the cosmic microwave background radiation, the afterglow of the Big Bang itself, the oldest light in the universe, released roughly 380,000 years after the beginning, when the cosmos had cooled enough for atoms to form and for light to travel freely through space. It had been traveling ever since, its wavelength stretched by the expansion of the universe from visible light to microwave radiation, filling every cubic centimeter of space with a faint, nearly uniform glow at a temperature of about 2.7 degrees above absolute zero. The two groups published their results simultaneously in the Astrophysical Journal in 1965. Penzias and Wilson described their observations in careful, understated language, noting only that a possible explanation for the signal was given by the Princeton team in a companion paper. The Princeton group, led by Dicke, and including Jim Peebles, Peter Roll, and David Wilkinson, provided the theoretical interpretation, connecting the observed signal to the predicted remnant radiation of the Big Bang. The discovery was a watershed. It transformed cosmology from a speculative philosophical pursuit into a precision science virtually overnight. To appreciate the significance of this moment, you have to understand what the cosmic microwave background actually is. In the very early universe, just moments after the Big Bang, all of space was filled with an incredibly hot, dense plasma, a roiling soup of protons, electrons, and photons, particles of light, all smashing into each other at tremendous speeds. The photons could not travel far without colliding with an electron, scattering in a random direction. The universe was opaque, like trying to see through a thick fog. But as the universe expanded, it cooled, and roughly 380,000 years after the Big Bang, the temperature dropped below about 3,000 degrees Kelvin, cool enough for protons and electrons to combine into neutral hydrogen atoms for the first time, an event physicists call recombination. Once the free electrons were captured into atoms, the photons were suddenly free to travel through space unimpeded. The fog lifted. The universe became transparent. Those photons have been traveling ever since. For 13.8 billion years, they have been streaming through the expanding universe. Their wavelengths stretched longer and longer by the expansion of space, shifting from the visible glow of a 3,000-degree surface down into the microwave region of the electromagnetic spectrum. Today, they fill every cubic centimeter of space with a faint, nearly uniform glow at a temperature of about 2.725 degrees above absolute zero, or about negative 454 degrees Fahrenheit. You cannot see them with your eyes, but if you could see in microwaves, the sky would glow uniformly in every direction, the afterglow of the birth of the universe itself. It is the oldest light in existence. Nothing older can be observed, because before recombination, the universe was opaque. The cosmic microwave background is, in a very real sense, the edge of the observable universe in time, a wall of light beyond which we cannot see. And it was this light that Penzias and Wilson stumbled upon, thinking it was noise in their equipment, thinking it might be pigeon droppings on their antenna. One of the most profound discoveries in human history began with two men scraping bird excrement off a radio horn in New Jersey. The confirmation of the Big Bang settled a debate that had been raging for decades. Since the late 1940s, two competing theories had vied for dominance in cosmology. The Big Bang model, developed by Gamow, Alpher, and Herman, held that the universe began in a hot, dense state and had been expanding and cooling ever since. The rival steady-state model, proposed in 1948 by Herman Bondi, Thomas Gold, and Fred Hoyle, held that the universe had no beginning and would have no end. It was eternal and unchanging in its large-scale properties to account for the observed expansion. The steady-state theorists proposed that new matter was continuously being created throughout space, filling in the gaps left by the receding galaxies, so that the average density of the universe remained constant over time. The steady-state theory was elegant, philosophically appealing, and supported by some of the most prominent astrophysicists of the era. Fred Hoyle, in particular, was a brilliant scientist and a fierce advocate for the model. It was Hoyle who, in his 1949 BBC radio broadcast, coined the term Big Bang as a dismissive label for the rival theory. He did not intend it as a compliment, and yet the name stuck, adopted by the very theory Hoyle sought to undermine. The cosmic microwave background was the decisive blow against the steady-state model. The steady-state theory had no natural mechanism for producing a uniform background of microwave radiation. The Big Bang theory, on the other hand, predicted it. The match between prediction and observation was devastating for the steady-state camp. By the early 1970s, the Big Bang was the accepted standard model of cosmology, and the steady-state theory, though never formally disproved in every detail, was abandoned by the mainstream scientific community. In the decades that followed, the cosmic microwave background was studied with increasing precision by a series of space missions that represented some of the most sophisticated scientific instruments ever built. In 1989, NASA launched the Cosmic Background Explorer, or COBE, a satellite designed to map the microwave background across the entire sky. COBE confirmed that the spectrum of the radiation matched a perfect blackbody curve, the characteristic shape predicted by the Big Bang theory. With extraordinary accuracy, it also detected tiny fluctuations in the temperature of the background, variations of about 1 part in 100,000. That were the seeds from which galaxies and clusters of galaxies would later grow. These results were followed by even more precise measurements from the Wilkinson Microwave Anisotropy Probe, or WMAP, launched by NASA in 2001, and from the Planck satellite, launched by the European Space Agency in 2009. Planck, in particular, produced a map of the cosmic microwave background of breathtaking detail and precision, measuring the temperature fluctuations across the sky with an accuracy that would have seemed impossible just a few decades earlier. The Planck results, published in a series of landmark papers beginning in 2013, provided the most precise determination of the fundamental parameters of the universe ever achieved. The data confirmed that the universe is 13.8 billion years old. It showed that the geometry of space is flat, or very nearly so, consistent with predictions from inflationary theory, and it measured the composition of the universe with remarkable precision. About 5% ordinary matter, about 27% dark matter, and about 68% dark energy, the mysterious component associated with the cosmological constant. These numbers are among the most important in all of science. They describe the universe we live in, the universe that Einstein spent his life trying to understand. And that 68%, that dominant component of dark energy, is the direct descendant of the cosmological constant that Einstein introduced in 1917, called his greatest blunder, and abandoned. The Big Bang model, enriched by the cosmological constant and dark matter, has been the reigning paradigm for a quarter of a century. It is known as lambda CDM, where lambda represents the cosmological constant and CDM stands for cold dark matter. It has successfully predicted a vast array of observations, from the temperature fluctuations in the cosmic microwave background to the large-scale distribution of galaxies, to the abundance of light elements forged in the first minutes after the Big Bang. It is one of the most successful and well-tested models in the history of science. And yet, despite all its success, there are cracks in the foundation. Cracks that may be pointing toward the next great revolution in our understanding of the cosmos. And in this triumphant picture of the cosmos that emerged from the mid-20th century, there was absolutely no need for Einstein's cosmological constant. The universe was expanding. The expansion was gradually slowing down due to gravity. And the only question that remained was whether the universe would expand forever, gradually coasting to a halt, or whether it would eventually stop and collapse back in on itself in a big crunch. Lambda, the embarrassing fudge factor, was assumed by almost everyone to be exactly 0. For the next 3 decades, from the mid-1960s through the late 1990s, the cosmological constant was treated as a historical curiosity, a cautionary tale about the dangers of letting philosophical prejudice override mathematics. Textbooks mentioned it briefly, usually as an example of how even the greatest minds can make mistakes. The standard model of cosmology had no place for it. But the universe, it turned out, had one more surprise in store. And it was going to bring lambda roaring back from the dead. In the late 1980s and early 1990s, two teams of astronomers embarked on an ambitious project. They wanted to measure exactly how fast the expansion of the universe was slowing down. Everyone agreed that the expansion was decelerating. Gravity, after all, pulls matter together, and the mutual gravitational attraction of all the matter in the universe should be gradually putting the brakes on cosmic expansion. The question was, how much deceleration? The answer would tell cosmologists the ultimate fate of the universe. The key to this measurement was a particular type of exploding star called a type Ia supernova. These are not ordinary stellar explosions. They occur in binary star systems, where a white dwarf, the dense remnant of a dead star, gradually siphons matter from a companion star. When the white dwarf accumulates enough mass, it reaches a critical threshold and detonates in a thermonuclear explosion of staggering power, briefly outshining an entire galaxy of billions of stars. Crucially, because the explosion is triggered at a specific mass threshold, all type Ia supernovae have roughly the same intrinsic brightness. Once small corrections are applied based on how their light curves fade over time, this makes them excellent standard candles. By comparing their known intrinsic brightness with their apparent brightness as seen from Earth, astronomers can calculate how far away they are. One team, the Supernova Cosmology Project, was led by Saul Perlmutter, an astrophysicist at the Lawrence Berkeley National Laboratory and the University of California, Berkeley. Perlmutter had begun building his team as early as 1988, and he had devised an ingenious observational strategy that allowed his group to guarantee batches of supernova discoveries on a predictable schedule, making it possible to secure time on the world's largest telescopes in advance. The rival team, the High-Z Supernova Search Team, was formed in 1994 by Brian Schmidt, an Australian-American astronomer who had earned his doctorate at Harvard. And it included Adam Rees, a young and exceptionally talented data analyst who led the team's analysis effort. The competition between the two groups was fierce, productive, and ultimately one of the most fruitful scientific rivalries of the 20th century. Both teams set out expecting to measure a decelerating universe. They would look at distant supernovae, calculate their distances, compare those distances with the galaxy's redshifts, and determine the rate at which the expansion was slowing. It should have been straightforward. What they found instead shook the foundations of physics. In 1998, the High-Z team, led by Rees's analysis, published their results. They had observed 10 type Ia supernovae at high redshifts, meaning they were looking at explosions that occurred billions of years in the past, when the universe was significantly younger than it is today. The distant supernovae were dimmer than expected, not by a lot, but by a consistent, measurable amount. Dimmer meant farther away than the decelerating models predicted. The universe was not slowing down, it was speeding up. Perlmutter later described the feeling of the discovery with a vivid analogy. Imagine throwing an apple into the air and expecting gravity to pull it back down. Instead, you watch as the apple accelerates upward and blasts off into space. That is what they were seeing, on the scale of the entire universe. The Supernova Cosmology Project, with its larger dataset of 42 high-redshift supernovae, published its results in 1999. Both teams had arrived at the same conclusion, independently. The expansion of the universe was accelerating. The scientific community was stunned. Something was pushing the universe apart, working against gravity on the largest scales, and getting stronger as the universe expanded. The physicist Michael Turner coined a name for this mysterious anti-gravity force: dark energy. And almost immediately, physicists realized what the simplest explanation for dark energy was. It was Einstein's cosmological constant, lambda. The term he had added to his equations in 1917, the term he had called his biggest blunder and discarded in the early 1930s, was exactly the kind of thing that could produce an accelerating expansion, a constant energy density permeating all of space, pushing outward, opposing the inward pull of gravity. As Saul Perlmutter himself later reflected, perhaps there was more insight in Einstein's so-called blunder than in the best efforts of ordinary mortals. Perlmutter, Schmidt, and Rees shared the 2011 Nobel Prize in Physics for their discovery of the accelerating expansion of the universe. The prize committee noted that the discovery had come as a complete surprise, even to the laureates themselves, and just like that, the cosmological constant was back. After nearly 7 decades in exile, lambda had returned to the field equations of general relativity, but this time, it was not a mathematical patch designed to produce a static universe. It was something far more profound, an intrinsic property of empty space itself, a vacuum energy that drives the accelerating expansion of the cosmos. But here is where the story takes an even stranger turn, because while the observational evidence for a non-zero cosmological constant is now overwhelming, confirmed by the cosmic microwave background measurements from the Planck satellite, by galaxy surveys, by gravitational lensing studies, and by ever more precise supernova observations, the theoretical understanding of what the cosmological constant actually is remains one of the deepest mysteries in all of physics. The problem has a name. It is called the cosmological constant problem, and it has been described by some physicists as the worst theoretical prediction in the history of science. Here is the issue. In quantum mechanics, empty space is not truly empty. It is a seething cauldron of activity. The quantum fields that permeate all of space are constantly fluctuating, with pairs of virtual particles popping into existence and annihilating each other in intervals too brief to observe directly. These fluctuations carry energy, a zero-point energy that is inherent to the vacuum itself. In the 1920s, the physicist Wolfgang Pauli was one of the first to notice that this vacuum energy should have gravitational effects. He calculated what would happen if you took vacuum energy seriously as a source of gravity, and found that the resulting cosmological constant would be so enormous that the observable universe, in Pauli's words, would not even reach the moon. The vacuum energy would have ripped spacetime apart long before any stars or galaxies could form. Pauli was reportedly amused by his own calculation, and nobody took it seriously at the time. But the problem did not go away. In the 1960s, the Soviet physicist Yakov Zeldovich was the first to formally calculate the value of the cosmological constant predicted by quantum field theory. He found that the vacuum energy should produce a cosmological constant that is absolutely enormous, dwarfing anything that astronomers had ever observed or could ever observe. The discrepancy between the theoretical prediction and the observed value is not a small one. It is not a factor of 10 or 100 or 1,000. It is a factor of 10 raised to the power of 120, one followed by 120 zeros. That is a number so large that there is no meaningful analogy to convey it. Think of it this way. If you predicted that a person weighs 200 pounds, and they actually weighed 200 pounds times 10 to the 120th power, your prediction would be off by more than the ratio between the smallest subatomic distance ever measured and the diameter of the entire observable universe. It is, quite simply, the largest discrepancy between theory and observation in the history of science. So either our understanding of quantum mechanics is profoundly wrong, or our understanding of gravity is profoundly wrong, or there is some as yet unknown mechanism that cancels out almost all of the vacuum energy, leaving behind just the tiny residual amount that we observe as the cosmological constant. And that cancellation would have to be precise to an almost inconceivable degree, like adjusting a dial with 120 digits and getting every single one of them exactly right. This is the cosmological constant problem, and despite decades of effort by some of the most brilliant theoretical physicists in the world, nobody has solved it. There are ideas, of course. One is called quintessence, a concept named after the fifth element of ancient Greek philosophy. In quintessence models, dark energy is not a fixed constant, but a dynamic field that changes over time and space. The term was formally introduced in a 1998 paper by Robert Caldwell, Rahul Dev, and Paul Steinhardt, though earlier work by Burrit Ratra and Jim Peebles in 1988, and by Christoph Wetterich in the same year, had explored similar ideas. If dark energy is quintessence rather than a true cosmological constant, its energy density would evolve over the history of the universe, potentially offering a more natural explanation for why its current value is so small compared to what quantum theory predicts. Another approach involves the idea of the multiverse, proposed most prominently by Steven Weinberg in the late 1980s. In this picture, there is not one universe, but an almost infinite number of them, each with a different value of the cosmological constant. Most of these universes would have vacuum energies so large that they would either expand to emptiness or collapse before anything interesting could happen. Only in the rare universes where the cosmological constant is very small, like ours, could galaxies, stars, planets, and observers come into existence. We see a small cosmological constant because we could not exist to observe a large one. This is a form of the anthropic principle, and many physicists find it deeply unsatisfying because it replaces explanation with selection, essentially saying that the value of lambda is not determined by any physical principle, but by the accident of which universe we happen to inhabit. And now, as we enter the mid-2020s, the story of the cosmological constant is entering what may be its most exciting chapter yet, because new observations are beginning to hint that the simplest version of the story, a cosmological constant that is truly constant, fixed, unchanging throughout the history of the universe, might not be the whole truth. The dark energy spectroscopic instrument, known as DAISY, is an ambitious international experiment designed to create the largest three-dimensional map of the universe ever made. Mounted on the 4-meter Mayall telescope at Kitt Peak National Observatory in Arizona, DAISY uses 5,000 robotic fiber positioners to simultaneously capture the spectra of thousands of galaxies and quasars. By measuring the baryon acoustic oscillations, ripples in the distribution of matter that were imprinted in the early universe by sound waves, DAISY can track how the expansion of the universe has changed over the past 11 billion years. In April of 2024, the DAISY collaboration released its first results based on the initial year of observations. The data showed subtle hints that dark energy might not be a strict cosmological constant after all. When combined with other measurements, including the cosmic microwave background data from the Planck satellite and supernova observations, the DAISY results suggested that the influence of dark energy might be weakening over time, becoming, as some scientists described it, less pushy. Then, in March of 2025, DAISY released its data release 2, based on 3 years of observations and more than double the data of the first release. The hints of evolving dark energy grew stronger, while the results are not yet at the 5 sigma threshold that physicists require to declare a definitive discovery. Some combinations of the DAISY data with other datasets reached as high as 4.2 sigma, approaching but not quite crossing the finish line. The DAISY spokesperson, Will Percival, noted that the simplest explanation for the data appeared to be shifting, and that modifying the standard model of cosmology to include evolving dark energy seemed increasingly promising. If confirmed, this would be monumental. It would mean that the dark energy driving the accelerating expansion of the universe is not a simple cosmological constant, not the static vacuum energy that Einstein imagined, but something dynamic, something that changes, something that may eventually weaken to the point where gravity regains the upper hand. The implications for the fate of the universe would be profound. Instead of an eternity of accelerating expansion, leading to a cold, dark, empty cosmos in which every galaxy has been pushed beyond the observable horizon, the universe might face a different destiny entirely. If dark energy weakens enough, the expansion could slow, stop, and perhaps even reverse. The ultimate fate of everything that exists hangs on the answer. At the same time, another profound mystery is intensifying: the Hubble tension, a discrepancy between two different methods of measuring the universe's expansion rate, has reached a level of statistical significance that many scientists now describe as a crisis. Measurements of the cosmic microwave background, when combined with the standard model of cosmology, predict an expansion rate of about 67.4 kilometers per second per megaparsec. But direct measurements using the cosmic distance ladder, involving Cepheid variable stars and type Ia supernovae, consistently yield a value closer to 73 kilometers per second per megaparsec. The difference, about 8 or 9%, might sound small, but both measurements are made with high precision, and the disagreement is now at the 5 sigma level, the gold standard for statistical significance. Something is wrong. Either there is a subtle, undetected error in one or both measurement methods, or there is something fundamentally incomplete about our understanding of the universe. Some physicists have proposed that the Hubble tension might be resolved by modifying the cosmological constant, perhaps allowing it to vary in ways we have not yet imagined. Others have suggested entirely new forms of physics, such as early dark energy, a hypothetical burst of repulsive energy that existed briefly in the young universe before fading away. And so here we are, more than a century after Einstein first scribbled lambda into his field equations. The cosmological constant remains at the very center of our deepest questions about the cosmos. What is the vacuum energy of empty space? And why is it so much smaller than our theories predict? Is dark energy truly constant, or is it evolving? What is driving the accelerating expansion, and will it continue forever? Can the Hubble tension be resolved? And if so, what new physics will be required? Einstein introduced the cosmological constant in 1917 because he could not accept the idea of a changing universe. He abandoned it in the early 1930s because the universe turned out to be changing after all. And for nearly 70 years, physicists assumed it was zero. But the universe had the last word. The cosmological constant is not zero. It is small, preposterously small compared to what our best theories of quantum mechanics predict, but it is not zero, and that tiny, non-zero value is the dominant component of the cosmos, the force that is shaping the ultimate destiny of everything that exists. Einstein called it his biggest blunder, but it may turn out to be his most profound insight, a glimpse, however accidental, into the deepest nature of space, time, and reality. The universe does not care about our expectations. It does not bend to our philosophies or our aesthetics. It simply is what it is. And what it is, we are only just beginning to understand. We are still peeling back the layers of this cosmic mystery, still following the trail of clues that Einstein set in motion over 100 years ago, still marveling at the strange and beautiful universe that lambda describes. The story is not over. In fact, given what Daisy and the next generation of telescopes are revealing, the most astonishing chapters may still lie ahead. But to truly understand the cosmological constant, to feel its weight and its significance, we need to go back further than the equations. We need to go back to the moment Einstein first sat down and asked himself what the universe looked like as a whole. Because the cosmological constant was not born out of idle mathematical curiosity. It was born out of a collision between the most powerful scientific theory ever conceived and the deepest philosophical assumptions a human being can hold about the nature of reality. Picture Berlin in the winter of 1916. The Great War is grinding on, consuming millions of lives in the mud and fire of the Western Front. Food is scarce. The city is gray and cold. And in a modest study, a man with wild hair and deeply shadowed eyes is staring at a set of equations that he has spent the last 10 years of his life trying to complete. He is Albert Einstein, and he has just achieved something that many of his contemporaries believed was impossible. The general theory of relativity, which Einstein had finalized in November of 1915, was more than just a new theory of gravity. It was a new theory of reality itself. In Newton's universe, space was a fixed, unchanging stage, and time was an absolute, universal clock ticking at the same rate for everyone, everywhere, forever. Einstein demolished this picture. Space and time, he showed, are not separate entities, but aspects of a single unified fabric, space-time. And this fabric is not fixed or rigid. It responds to the presence of matter and energy. It bends, it stretches, it curves, it can even ripple, sending waves of distorted geometry, propagating across the cosmos at the speed of light. The mathematical framework Einstein used to describe this was a branch of geometry developed in the 19th century by the German mathematician Bernhard Riemann. Riemannian geometry describes curved spaces of arbitrary dimensionality. spaces where the rules of ordinary Euclidean geometry, the geometry you learned in school with flat surfaces and right angles, no longer apply. In Riemannian geometry, the shortest path between 2 points is not necessarily a straight line. It might be a curve, a geodesic, bending through the warped landscape of the geometry itself. Einstein's genius was to realize that this mathematical framework could describe the physical universe. The geodesics of curved spacetime are the paths that objects follow under the influence of gravity. The curvature of spacetime at any point is determined by the distribution of mass and energy at and around that point. The relationship between matter and geometry is captured in the Einstein field equations, a set of 10 coupled nonlinear partial differential equations that are simultaneously beautiful and terrifyingly difficult to solve. But Einstein was not content to describe gravity near a single star or planet. He wanted to describe the entire universe. And so, in early 1917, just over a year after completing General Relativity, he turned his attention to cosmology. The task he set himself was clear. He wanted to find a solution to his field equations that described a universe filled with matter, a universe that was spatially finite but without boundaries, like the surface of a sphere but in 3 dimensions, a universe that was static and eternal, and a universe that was consistent with Mach's principle. This last condition was particularly important to Einstein, and it requires some explanation. Ernst Mach, the Austrian physicist and philosopher, had argued in the 19th century that the inertia of any object, its resistance to changes in motion, is not an intrinsic property of the object itself, but is instead determined by the influence of all the other matter in the universe. In other words, a spinning bucket of water develops a concave surface, not because of some absolute quality of rotation, but because of its relationship to distant stars. Take away the stars, and the concept of rotation would become meaningless. Einstein was deeply attracted to this idea. He believed that his theory of general relativity should embody Mach's principle, that spacetime itself should have no existence independent of the matter it contains. A universe devoid of matter should have no geometry, no structure, no meaning. This was not just a scientific requirement for Einstein. It was almost a philosophical or aesthetic one. The universe should be self-contained. Space and time should emerge from matter, not exist apart from it. But when Einstein applied his field equations to a universe uniformly filled with matter, he ran into a problem that struck at the heart of these convictions. The equations did not allow for a static universe. Depending on the details, the universe either expanded or contracted. There was no equilibrium. Gravity, the universal attractive force described by general relativity, inexorably pulled all the matter in the universe together. Left to its own devices, a universe filled with matter would collapse. This was not just a mathematical inconvenience. It was, for Einstein, a conceptual crisis. The idea of a universe that changed on the largest scales, that had some kind of cosmic evolution, was simply outside the range of what he was willing to contemplate. And remember, in 1917, there was no observational evidence for anything other than a static cosmos. The astronomical observations of the day, limited primarily to stars within our own galaxy, were entirely consistent with a universe that had always existed in more or less its current state. So Einstein did what scientists sometimes do when the math tells them something they do not want to hear. He adjusted the math. He modified the left-hand side of his field equations by adding a new term. This term contained a new constant, which he denoted by the Greek letter lambda, and it was multiplied by the metric tensor, the mathematical object that encodes the geometry of spacetime. The effect of this term was to introduce a kind of repulsive force that grew with distance. At small scales, within the solar system, or even within galaxies, the lambda term was negligible, its effects dwarfed by ordinary gravity. But on the scale of the entire universe, the cosmological constant could balance gravity exactly, producing the static, unchanging cosmos that Einstein desired. He was not comfortable with this addition. In a letter to his friend Paul Ehrenfest, Einstein described the cosmological constant with evident distaste. He later wrote that the term had always given him a bad conscience. He called it ugly, artificial, inelegant, and yet he saw no alternative. Without it, his beautiful theory predicted a universe that was impossible, at least by the standards of what he was willing to believe. His paper, presented to the Prussian Academy of Sciences on the 8th of February, 1917, was titled Cosmologische Betrachtungen zur allgemeinen Relativitätstheorie, or Cosmological Considerations in the General Theory of Relativity. In it, Einstein described a universe shaped like the three-dimensional analog of a sphere's surface, finite in volume, but without edges or boundaries. Matter was distributed uniformly throughout this space, and the cosmological constant was carefully tuned to keep the whole thing in perfect balance. There was a simple mathematical relationship at the heart of his model. The cosmological constant, the density of matter, and the radius of the universe were all connected. Given the density of matter, you could calculate the size of the universe and the value of lambda. It was elegant in its way, a self-consistent, closed system, a universe that was everything Einstein wanted it to be. But there was a fatal flaw that Einstein did not notice. His static universe was unstable. It was balanced, yes, but in the same way that a ball balanced on the tip of a needle is balanced. The slightest perturbation, the tiniest increase or decrease in the density of matter at any point, would throw the system out of equilibrium. If the universe expanded even slightly, the matter density would decrease. The repulsive effect of the cosmological constant would gain the upper hand, and the expansion would accelerate. If the universe contracted slightly, the matter density would increase. Gravity would overwhelm the cosmological constant, and the contraction would accelerate. Einstein's static universe was perched on a knife edge. It was, in the language of physics, a state of unstable equilibrium. Why Einstein failed to notice this instability is one of the enduring puzzles in the history of physics. He was, after all, one of the greatest minds who ever lived, and the instability is not particularly subtle. Several historians have suggested that Einstein was so focused on achieving a static solution that he simply did not bother to check whether the solution was stable. Others have speculated that his philosophical commitments to Mach's principle and a static cosmos blinded him to the mathematical warning signs. Whatever the reason, the instability would remain undiscovered until it was pointed out by Arthur Eddington in 1930, more than a decade later. And it was not just the instability that was problematic. Almost immediately after Einstein's paper was published, the Dutch astronomer Willem de Sitter discovered an alternative solution to the modified field equations that was deeply troubling for Einstein's entire program. De Sitter, working at the Leiden Observatory, showed that the field equations with the cosmological constant admitted a solution for a universe that was entirely empty. No matter at all, just the cosmological constant and the geometry of spacetime. In de Sitter's universe, spacetime had properties. It had curvature, it had dynamical behavior, even though it contained not a single particle of matter. This was a direct assault on Mach's principle. If spacetime could exist and have geometric properties without any matter to cause them, then the whole idea that matter determines the structure of spacetime was fatally undermined. Einstein and de Sitter exchanged a series of letters in 1917 and 1918, debating the physical meaning of de Sitter's solution. Einstein argued that the solution was not physically realistic, that it was merely a mathematical artifact with no bearing on the real world. De Sitter countered that a physically valid theory should not produce unphysical solutions, and that if it did, the theory itself might need revision. There was another intriguing feature of de Sitter's empty universe. If you introduced a test particle, a tiny speck of matter, into the de Sitter spacetime, that particle would appear to recede from an observer. The farther away it was, the faster it would appear to move. This was a prediction of cosmic redshift, a systematic reddening of light from distant objects that emerged naturally from the mathematical structure of de Sitter's solution. It would take another decade before this prediction found observational support. But in hindsight, it was a remarkable hint that the universe was not as static as Einstein believed. Meanwhile, the early observational evidence was slowly accumulating. The American astronomer Vesto Slipher, working at the Lowell Observatory in Flagstaff, Arizona, had been measuring the spectra of spiral nebulae since 1912. By 1917, he had found that the vast majority of these nebulae showed redshifted spectral lines, indicating that they were moving away from us at significant speeds. Some were receding at hundreds, even thousands, of kilometers per second. Slipher's results were known in the astronomical community, but their cosmological implications were not yet understood. Nobody knew for certain whether the spiral nebulae were separate galaxies far beyond our own Milky Way, or just nearby clouds of gas. The answer to that question would come from Edwin Hubble, and it would change everything. But before Hubble, there was Friedman. And the story of Friedman deserves a more careful telling, because his contribution to cosmology was not just technically important, but deeply human. Alexander Friedman's life was marked by extraordinary contrasts. Born into an artistic family in the capital of Imperial Russia, he grew up surrounded by music and culture. But he chose the austere life of mathematics and physics. He was a patriot who volunteered for military service, flying dangerous missions over enemy territory during the First World War. He was also a scholar of the deepest kind, someone who could peer into the mathematical structure of Einstein's equations and see things that Einstein himself had missed. When Friedman turned his attention to cosmology in 1922, he was not motivated by any particular astronomical observation. He was motivated by pure mathematical curiosity. What happens, he asked, if we do not assume that the universe is static? What if we let the equations speak for themselves? What does general relativity actually predict for a universe filled with matter? The answer, Friedman found, was a universe of extraordinary variety. By varying the cosmological constant and the spatial curvature, he could produce universes that expanded forever, universes that expanded and then contracted, universes that oscillated between expansion and contraction, and, as a very special case, universes that sat in Einstein's unstable static balance. The key insight was that a static universe was not the natural state of things. It was an anomaly, a precarious exception to the general rule that a universe governed by gravity must either be growing or shrinking. Friedman published his results in two papers in 1922 and 1924. The first, on the curvature of space, dealt with the case of positive spatial curvature, a universe shaped like a higher dimensional sphere. The second, on the possibility of a world with constant negative curvature of space, extended the analysis to negatively curved and flat geometries. Together, they constitute the mathematical foundations of modern cosmology. Einstein's reaction to Friedman's first paper is one of the most telling episodes in the history of science. When he received the paper, Einstein published a quick note claiming that Friedman had made a mathematical error. He was wrong. The error was Einstein's. When this was pointed out to him, Einstein published a retraction acknowledging that Friedman's mathematics was correct, but he added a dismissive comment that the results had no physical significance. Einstein simply could not accept that the universe was expanding, and he allowed this conviction to color his scientific judgment. Friedman never lived to see his predictions confirmed. He died in September of 1925, at the age of 37, probably from typhoid fever contracted after a balloon flight. He had spent the last years of his life in a whirlwind of activity, teaching, researching, exploring, always pushing at the boundaries of the known. A biography of Friedman published decades later summed up his contribution with a beautiful analogy. As Copernicus made the Earth go round the sun, so Friedman made the universe expand. 2 years after Friedman's death, and entirely independently, Georges Lemaître arrived at the same mathematical conclusions. But Lemaître, unlike Friedman, was not content with abstract mathematics. He was a physicist and an astronomer, and he wanted to connect the theory to observations. Lemaître was an extraordinary figure. A man of deep faith and equally deep scientific rigor, he navigated the relationship between religion and science with remarkable grace. He insisted throughout his life that the physical beginning of the universe, as described by his theory, was entirely separate from the theological concept of creation. They were, in his view, different questions that demanded different methods. Science could tell you how the universe began. It could not tell you why. His 1927 paper, published in French in the obscure Annales de la Société Scientifique de Bruxelles, was a masterpiece of synthesis. Lemaître took the mathematical framework of general relativity, applied it to a universe filled with matter, and derived an expanding solution. He then connected this solution to the observed redshifts of distant galaxies, showing that the recession of the galaxies was a natural consequence of the expansion of space itself. He even calculated a relationship between distance and recession velocity that was equivalent to what Hubble would publish 2 years later. It is one of the great injustices of scientific history that Lemaître's paper was largely ignored at the time. It was written in French, published in a journal that few international physicists read, and its author was a young, relatively unknown Belgian priest. When Lemaître presented his results to Einstein at the 1927 Solvay conference, Einstein dismissed them with the stinging remark about abominable physics. It would take several more years, and the overwhelming observational evidence provided by Hubble before the expanding universe gained widespread acceptance. Hubble's work at Mount Wilson deserves its own detailed telling, because it was not just a theoretical breakthrough, but an observational triumph, built on years of painstaking, meticulous work with the most powerful telescope in the world. The 100-inch Hooker telescope at Mount Wilson was a marvel of engineering. Its primary mirror, a disk of glass 100 inches in diameter and weighing 4.5 tons, had been poured at a glass factory in Saint-Gobain, France, and shipped across the Atlantic to California, where it was ground and polished to exquisite precision. The telescope sat in a dome atop Mount Wilson, 5,700 feet above the growing city of Los Angeles. On clear nights, the seeing, as astronomers call the quality of the atmospheric conditions, was superb, and the telescope could resolve individual stars in galaxies millions of light-years away. Hubble spent years with this instrument, carefully photographing the sky, identifying individual stars in distant nebulae, measuring their brightness, and calculating their distances. His collaborator, Milton Humason, was an indispensable partner in this work. Humason had an extraordinary life story. He had dropped out of school at 14 to work as a mule driver on Mount Wilson, hauling equipment up the mountain for the observatory's construction. He later became a janitor at the observatory, then a night assistant, and finally, through sheer skill and dedication, a full-fledged astronomer. His ability to obtain high-quality spectra of faint, distant galaxies was legendary, and his contributions to the discovery of the expanding universe were immense. By 1929, Hubble had enough data to plot his famous graph. The horizontal axis showed the estimated distances to 24 galaxies and clusters. The vertical axis showed their recession velocities, derived from the redshifts measured primarily by Slipher and Humason. The data points scattered upward from left to right, and through them, Hubble drew a straight line. The slope of that line was what we now call the Hubble constant, a measure of the rate at which the universe is expanding. Hubble's original estimate of the Hubble constant was about 500 kilometers per second per megaparsec, far higher than the modern value of around 70. This large error was due to systematic problems with the distance measurements, particularly the failure to distinguish between different types of Cepheid variable stars with different intrinsic luminosities. These errors would not be corrected for decades by astronomers like Walter Baade and Alan Sandage, but the essential conclusion was robust. The universe was expanding. Galaxies were moving apart. Space itself was growing. The impact on Einstein was immediate and profound. Upon learning of Hubble's results, Einstein traveled to Mount Wilson in 1931. He met Hubble. He looked through the great telescope, and he came away convinced the universe was not static. It was expanding. And if the universe was expanding, there was no need for the cosmological constant. Lambda had been introduced solely to prevent the expansion that was actually happening. It was, in a word, unnecessary. In a series of papers published in the early 1930s, Einstein dropped the cosmological constant from his equations. In one model, developed jointly with de Sitter in 1932, he considered an expanding universe with zero cosmological constant and zero spatial curvature, a model that became known as the Einstein-de Sitter universe and served as the standard cosmological model for decades. And so the cosmological constant entered its long exile. From the early 1930s to the late 1990s, a span of nearly 70 years, most physicists assumed that lambda was exactly zero. The universe was expanding. The expansion was slowing down due to gravity. And the only interesting question was the rate of deceleration. The cosmological constant was mentioned in textbooks, briefly, usually accompanied by a cautionary anecdote about Einstein's blunder. It was a footnote, a curiosity, a dead idea. But even during this long dormancy, there were murmurs, hints, whispers from the data that something was not quite right. In the 1960s and 70s, astronomers struggled to reconcile the observed age of the oldest stars with the predicted age of the universe in models without a cosmological constant. The stars seemed to be older than the universe, an obvious impossibility. A small but non-zero cosmological constant could resolve the discrepancy by making the universe older than the zero lambda models predicted. But the evidence was not compelling enough to overturn the prevailing consensus. In the 1980s, the development of inflationary theory by Alan Guth, Andre Linde, and others added a new wrinkle. Inflation proposed that in the first tiny fraction of a second after the Big Bang, the universe underwent a period of exponentially rapid expansion, driven by a form of energy remarkably similar in its mathematical description to the cosmological constant. During inflation, the universe expanded by a factor of at least 10 to the 26th power in a time interval of about 10 to the negative 36 seconds. This inflationary expansion was driven by the energy of a hypothetical field called the inflaton, and it smoothed out the universe, flattened its geometry, and produced the tiny density fluctuations that would later grow into galaxies and clusters of galaxies. The inflaton field energy was, in essence, a temporary cosmological constant, an enormous one that dominated the universe for a brief instant, and then decayed away, releasing its energy as the hot, dense plasma of the Big Bang. This showed that cosmological constant-like physics was not just a mathematical abstraction. It had likely played a crucial role in the earliest moments of cosmic history. And then, in the late 1980s, tantalizing hints appeared in the data. Measurements of the cosmic microwave background, combined with observations of galaxy clustering and the distribution of large-scale structures, seemed to point toward a universe in which the total energy density was equal to the critical density, consistent with a flat geometry, as inflation predicted. But the total amount of matter, both ordinary and dark, appeared to account for only about 30% of this critical density. Something was missing. 70% of the universe's energy budget was unaccounted for. Some theorists began to wonder if the missing component might be vacuum energy, a small, positive cosmological constant, lambda. And then came 1998, the discovery of the accelerating expansion by the two supernova teams is worth dwelling on, because it was not just a discovery, but a genuinely shocking event in the history of science. These were not people looking for dark energy. They were looking for the rate of deceleration. They fully expected to find that the expansion of the universe was slowing down. They had designed their experiments, built their teams, and secured their telescope time on the assumption that gravity was gradually putting the brakes on cosmic expansion. Finding acceleration was like looking for a gentle headwind and discovering a hurricane at your back. Adam Rees later described the experience of analyzing the data and realizing what it was telling him. He checked his code over and over looking for errors. He reran the analysis with different assumptions. He consulted with colleagues. Every time, the answer was the same. The distant supernovae were too dim. They were farther away than they should have been in a decelerating universe. The expansion was speeding up. Saul Perlmutter's team went through a similar process of incredulity and verification. They had been gathering data for nearly a decade, and they had developed sophisticated techniques for finding and measuring distant supernovae. When their analysis pointed to an accelerating expansion, they too spent months checking and rechecking before going public. The fact that two independent teams, using somewhat different methods and different datasets, arrived at the same conclusion was crucial. If only one team had found the result, it might have been dismissed as a fluke or a systematic error, but the agreement between the two rivals made the conclusion far more robust. Science, at its best, is a self-correcting enterprise, and the competition between the Supernova Cosmology Project and the High-Z Supernova Search Team is a perfect example. The reaction of the scientific community was a mixture of shock, excitement, and deep unease. An accelerating expansion meant that something was working against gravity on the largest scales, something with a repulsive gravitational effect. The simplest mathematical description of such a thing was Einstein's cosmological constant. Lambda was back. But as we have discussed, the return of the cosmological constant brought with it the enormous puzzle of vacuum energy. And it is worth spending more time with this puzzle, because it is not just a technical problem for specialists. It is one of the most profound questions in all of science. The vacuum, in quantum mechanics, is not nothing. It is a state of minimum energy, the ground state of the quantum fields that permeate the universe. But even in this ground state, the fields are not quiet. They are fluctuating, vibrating, producing what physicists call zero-point energy. This is not a theoretical speculation. It is an experimentally verified fact. The Casimir effect, in which two metal plates placed very close together in a vacuum are pushed toward each other by the pressure of the vacuum fluctuations, has been measured in laboratories to high precision. The Lamb shift, a tiny difference in the energy levels of hydrogen atoms caused by the interaction of the electron with the fluctuations of the electromagnetic field, has been measured with astonishing accuracy. The vacuum is real. Its energy is real. And in principle, that energy should gravitate. The problem is that when you calculate how much energy the vacuum should contain, you get an answer that is absurdly, catastrophically large. The calculation depends on assumptions about the highest energy scales in physics. But no matter how you do it, the answer dwarfs the observed value of the cosmological constant by tens or hundreds of orders of magnitude. If the vacuum energy were as large as quantum field theory naively predicts, the universe would have been ripped apart or crushed into nothingness long before any stars or galaxies could form. The physicist Antonio Padilla of the University of Nottingham, who has spent nearly 2 decades working on this problem, has called it one of the most awkward, embarrassing, difficult problems in theoretical physics today. And he is not alone. A survey of theoretical physicists would reveal near universal agreement that the cosmological constant problem is one of the deepest, most stubborn, most important unsolved problems in fundamental physics. There is one more dimension to this story that brings it squarely into the present. And that is the possibility that we are on the verge of discovering that the cosmological constant is not, in fact, constant. The Dacey results of 2024 and 2025 have sent ripples of excitement through the cosmological community. If dark energy is evolving, if it is getting weaker over time, then it is not a simple cosmological constant. It is something else. It might be quintessence, the dynamic scalar field proposed in the late 1990s. It might be something entirely new, something that our current theories do not even have a name for. Carlos Frank, a professor at Durham University, told The Guardian that if the Daisy hints are confirmed, our previous understanding of the universe goes out the window. We would have to start from scratch, revising our understanding of basic physics, the Big Bang, and the long-range forecast for the cosmos. This is not hyperbole. The standard model of cosmology, known as lambda CDM, with its cosmological constant and its cold dark matter, has been the reigning paradigm for a quarter of a century. It has successfully predicted the cosmic microwave background, the large-scale structure of the universe, the abundance of light elements, and a host of other observations. If it needs to be modified, the implications would be enormous. And then there is the Hubble tension, which adds another layer of complexity. The fact that two different methods of measuring the expansion rate give incompatible answers suggests that something is wrong with our cosmological model. Some physicists have proposed that the Hubble tension might be related to the nature of dark energy. If dark energy is not a simple cosmological constant, but something more complex, something that behaves differently at different cosmic epochs, it might help reconcile the discrepant measurements. As of early 2026, the Hubble tension remains unresolved. Data from the James Webb Space Telescope has confirmed that earlier Cepheid measurements were accurate, ruling out one potential source of error. New measurement techniques, including surface brightness fluctuations and gravitational lensing time delays, continue to yield values in the 70 to 74 range, in tension with the Planck value of about 67.4. The European Space Agency's Euclid mission is gathering data that may provide an independent perspective when its primary results are published. And the Daisy collaboration continues to collect spectra, with its full 5-year dataset expected to provide much more definitive answers about whether dark energy is evolving. We stand right now at one of the most exciting moments in the history of cosmology. The questions we are asking are the same ones that Einstein grappled with in 1917. What is the universe made of? How does it behave? What is its fate? But we are asking them with tools and data that Einstein could never have imagined. Space telescopes, robotic fiber positioners, detectors sensitive enough to measure the faint glow of the cosmic microwave background to 1 part in 100,000, supercomputers that can simulate the evolution of the universe from the Big Bang to the present day. And at the center of it all, like a thread running through the entire history of modern cosmology, is the cosmological constant, that one small term, that one Greek letter, that Einstein added to his equations in a moment of philosophical stubbornness and later rejected in a moment of scientific humility. It has been dead and resurrected. It has been called the worst prediction in physics and the most profound mystery in science. It has been embraced and abandoned, mocked and vindicated. And still, after more than a century, nobody knows what it really is. There is a profound lesson in this story, one that goes beyond the specifics of cosmology and touches on the nature of science itself. Einstein's cosmological constant was introduced for the wrong reasons, to prop up a static universe that does not exist. It was abandoned for the wrong reasons too, discarded because the expanding universe seemed to make it unnecessary. And it came back for reasons that nobody anticipated, because the expansion is not just continuing, but accelerating. The universe does not care about our reasons. It does not care about our philosophies, our prejudices, our aesthetic sensibilities. It simply is. And the job of science is not to tell the universe what it should be, but to listen carefully and humbly to what it is telling us. Einstein listened, eventually. When the evidence for expansion became overwhelming, he changed his mind. He dropped the cosmological constant. He embraced the expanding universe. He acknowledged that Friedman and Lemaitre had been right, and he had been wrong. This is not a failure. This is science at its best. The willingness to be wrong, to change course, to follow the evidence wherever it leads, even into territory that feels strange and uncomfortable and impossible. And now, as a new generation of scientists follows the evidence into even stranger territory, the cosmological constant continues to challenge, to provoke, to inspire. It is, in some sense, the single most important number in the universe. A number that describes the energy of empty space, the fate of the cosmos, the balance between expansion and contraction, between existence and oblivion. We do not know its origin. We do not know why it has the value it does. We do not even know with certainty whether it is truly constant or whether it is changing. But we know it is there. We can measure it. We can observe its effects. And we know that understanding it, truly understanding it, will require a revolution in physics as profound as the ones Einstein himself ignited, perhaps somewhere in a universe that is expanding, accelerating, and filled to the brim with an energy that defies our deepest theories. Perhaps somewhere in all of that cosmic mystery, Einstein is smiling because the biggest blunder of his life turned out to be a window into the deepest secret of the cosmos, and we are still looking through it. But before we leave this extraordinary story, there are deeper layers still to explore, because the cosmological constant is not just a number in an equation. It is the meeting point of the two greatest theories in physics, general relativity and quantum mechanics, and the fact that they disagree so violently about its value is telling us something profound about the limits of our understanding. Let us sit with the cosmological constant problem for a moment longer, because it deserves more than a passing mention. It is, in many ways, the most important unsolved problem in all of theoretical physics, and the story of how we came to recognize it is a story of slowly dawning horror. When Einstein first introduced the cosmological constant in 1917, he thought of it as a simple geometric property of spacetime, a curvature term that could be added to his field equations without violating any mathematical principle. He did not connect it to the energy of the vacuum. That connection came later, as quantum mechanics matured. In the 1920s and 1930s, physicists were building the framework of quantum field theory, the mathematical language that describes particles and forces in terms of quantized fields. One of the first things they noticed was that the ground state of these fields, the state with the lowest possible energy, was not zero energy. It was a finite, positive amount. This zero-point energy was an unavoidable consequence of Heisenberg's uncertainty principle, which states that you cannot simultaneously know the exact position and momentum of a particle with perfect precision. The more precisely you pin down one, the less precisely you know the other. Applied to quantum fields, this means that the fields can never be perfectly still. They must always be fluctuating, even in the vacuum, and those fluctuations carry energy. In flat spacetime, without gravity, this vacuum energy has no observable consequences. You can simply define it away, setting the zero of your energy scale wherever you like. But in general relativity, all forms of energy gravitate. You cannot ignore the vacuum energy because it contributes to the curvature of spacetime. And so, the vacuum energy of quantum field theory becomes, in the context of general relativity, a contribution to the cosmological constant. The problem is quantitative. When you calculate the vacuum energy by summing up the contributions of all the quantum fluctuations across all the fields, and all the energy scales up to the Planck scale, the energy at which quantum gravity effects are expected to become important, you get a number that is grotesquely large. The calculation involves an integral that technically diverges, goes to infinity. But even if you impose a cutoff at the Planck energy, the result is about 120 orders of magnitude larger than the observed cosmological constant. Now, 120 orders of magnitude is not a number that human intuition can grasp. So let me try to illustrate it differently. Imagine you have a bathtub and you want to fill it with exactly 1 teaspoon of water, but your faucet, when you turn it on, produces not a trickle but a torrent with a flow rate of 10 to the 120th teaspoons per second. You need to turn it on just barely, for an infinitesimally brief instant, and then shut it off with perfect precision, capturing exactly 1 teaspoon and not a drop more. Miss by the tiniest fraction, and you flood not just your bathroom, but your house, your city, your planet, your galaxy, and every galaxy in the observable universe, all with water. That is the level of fine-tuning required to make the theoretical vacuum energy match the observed cosmological constant. It is, to put it mildly, unsatisfying. Several approaches to resolving this problem have been proposed, and each has its own strengths and weaknesses. One idea is supersymmetry, a theoretical framework that predicts a symmetry between the two fundamental classes of particles in nature, bosons, which carry forces, and fermions, which make up matter. In a perfectly supersymmetric universe, the vacuum energy contributions from bosons and fermions would cancel each other out exactly, producing a cosmological constant of precisely 0. This is an appealing idea because it provides a principled reason for the cancellation rather than relying on fine-tuning. The problem is that we know our universe is not perfectly supersymmetric. Supersymmetry, if it exists, must be broken at energies accessible to particle accelerators. And broken supersymmetry does not produce a 0 cosmological constant. It produces a very large one, bringing us back to the same problem. Another approach is the anthropic argument, championed most prominently by Steven Weinberg, one of the 20th century's greatest theoretical physicists. In a remarkably prescient paper published in 1987, Weinberg argued that if the cosmological constant could take a range of values in different regions of a vast multiverse, then observers like us could only exist in regions where the value was small enough to allow the formation of galaxies and stars. Weinberg used this reasoning to predict that the cosmological constant should be small, but non-zero, with a value of roughly the right order of magnitude. When the accelerating expansion was discovered 11 years later, many physicists were struck by the accuracy of Weinberg's prediction. But the anthropic argument is controversial. It does not explain why the cosmological constant has the value it does in any mechanistic sense. It simply notes that values much larger or much smaller would be incompatible with our existence. Many physicists regard this as giving up on explanation, replacing understanding with selection. Others see it as a perfectly reasonable application of the same logic that explains why we live on a habitable planet, rather than in the vacuum of interstellar space. We could not exist anywhere else. A third line of attack involves modifications to general relativity itself. Perhaps Einstein's theory, for all its triumphs, is not the final word on gravity. Perhaps at very large scales, or at very high energies, or in the presence of dark energy, the field equations need to be modified in ways that naturally produce a small, effective cosmological constant. This is an active area of research, with many competing proposals, but no consensus has yet emerged. And then there is the possibility that the whole problem is simply a misunderstanding. Perhaps the way we calculate the vacuum energy in quantum field theory is fundamentally flawed when applied to curved spacetime. Perhaps there is a deeper, more careful treatment that avoids the divergences and produces a sensible, small answer. Some researchers have argued along these lines, suggesting that the cosmological constant problem is an artifact of misapplied classical reasoning, rather than a genuine conflict between quantum mechanics and gravity. But this view remains a minority position. The truth is that we do not know. After nearly 60 years of work on the cosmological constant problem, since Zeldovich's calculations in the 1960s, we are not significantly closer to a solution than we were at the beginning. The problem is waiting for a breakthrough. Perhaps a new symmetry principle, perhaps a new formulation of quantum gravity, perhaps a new way of thinking about spacetime and the vacuum that has not yet been conceived. And perhaps the Dacey results are pointing us in the right direction. Because if dark energy is not a simple cosmological constant, but a dynamical field, then the cosmological constant problem takes on a different character. Instead of asking why the vacuum energy is so small, we might need to ask why a dynamical field has the properties it does, and what physics determines its evolution. This is still a hard question, but it is a different hard question, and different questions sometimes lead to different, more productive lines of investigation. The interplay between theory and observation is the engine that drives progress in cosmology. Einstein's theoretical work in 1915 and 1917 launched modern cosmology. Hubble's observations in 1929 confirmed the expanding universe. Penzias and Wilson's accidental detection of the cosmic microwave background in 1964 confirmed the Big Bang. And the supernova team's discovery of the accelerating expansion in 1998 resurrected the cosmological constant and opened an entirely new chapter in our understanding of the cosmos. Each of these milestones involved a dialogue between what we thought we knew and what the universe was actually doing. Each required scientists to change their minds, sometimes reluctantly, sometimes with astonishment, sometimes with the quiet satisfaction of seeing a long-held suspicion confirmed, and each left behind new mysteries that the next generation of scientists would need to tackle. We are now in the middle of another such dialogue. The data from Dacey, from the James Webb Space Telescope, from the Euclid mission, from ground-based galaxy surveys, and from gravitational wave observatories are painting an increasingly detailed picture of the cosmos. And that picture is not entirely consistent with the standard model of cosmology. There are hints of new physics, hints of a universe that is more complex and more surprising than the neat and tidy lambda CDM model suggests. Whether those hints will grow into definitive discoveries remains to be seen. DACY's full 5-year dataset will provide much more statistical power. Euclid, which launched in July of 2023 and is currently mapping the dark universe with unprecedented precision, will provide independent measurements of the expansion history and the growth of cosmic structure. The Vera C. Rubin Observatory, with its 8-meter telescope and enormous field of view, will survey billions of galaxies and discover hundreds of thousands of supernovae, providing a flood of new data for cosmological analysis. And future gravitational wave observatories, both on the ground and in space, will open an entirely new window on the universe, potentially revealing the behavior of dark energy through the merging of neutron stars and black holes at cosmological distances. The next decade promises to be one of the most exciting in the history of cosmology. The questions are old as human curiosity itself. But the tools are new, and the answers they are providing are turning out to be more strange, more beautiful, and more challenging than anyone expected. And through it all, running like a golden thread through the entire story, is Einstein's cosmological constant. That one small term, born of frustration and philosophical conviction in a cold Berlin study in 1917, abandoned in embarrassment in the early 1930s, ignored for 7 decades, resurrected by the astonishing discovery of the accelerating expansion, and now, in the 2020s, being scrutinized more intensely than ever, as new observations hint that it may not be the simple, unchanging constant that the standard model assumes. It is a story that spans more than 100 years of human effort, from Friedman's lonely calculations in revolutionary Petrograd to the robotic fiber positioners of DACY, scanning the sky from a mountaintop in Arizona. It is a story of genius and stubbornness, of brilliant predictions and spectacular mistakes, of accidental discoveries and decades of patient observation. It is a story that is still unfolding, still revealing new surprises, still defying our expectations. The cosmological constant is more than a number. It is a symbol of our relationship with the universe, a reminder that the cosmos is under no obligation to make sense to us, a testament to the power of mathematics to reveal truths that our intuition cannot grasp, and a promise that, no matter how much we learn, there will always be more to discover. Einstein would have appreciated the irony. His greatest blunder became his most enduring legacy. The thing he tried to erase from his equations turned out to be the dominant component of the universe. And the question he spent his life trying to answer, what is the nature of space, time, and gravity, remains as open and as urgent as ever. Look out at the night sky, and you are looking through a cosmos that is 70% dark energy. Every photon that reaches your eyes has traveled through an expanding, accelerating universe, pushed along by a force that Einstein imagined, rejected, and that we still do not understand. We are surrounded by it, immersed in it, shaped by it. And we are slowly, painfully, beautifully beginning to comprehend it. That is the power of science. Not certainty, but the courage to be uncertain. Not answers, but better questions. Not a final truth, but an endless, exhilarating search for understanding. And the cosmological constant, Einstein's reluctant invention, stands at the very heart of that search. If you enjoyed this deep dive into one of the most remarkable stories in the history of science. Please take a moment to like this video, subscribe to the channel, and share it with someone who loves the cosmos as much as we do. Drop a comment below with your thoughts. Do you think dark energy is changing? Is the Hubble tension a sign of new physics? What do you think Einstein would say if he could see the universe today? We would love to hear from you. Thanks for spending this time with us, and we will see you next time.